Today I'd like to spend just a couple minutes talking about small signal analysis, only to kind of preempt where we're heading in regard to modeling of MOS transistors. But I will spend almost all the period talking about a bulk CMOS process flow. So a review from last week. We spent a lot of time modeling MOS transistors. So if we look at the number of different MOS transistor models we have a switch level model, two of them, an ideal switch level model and one with the resistance and capacitance in it. Then we have a square law model. And then we had a square law model with lambda and bulk additions. And then we had an alpha law model. The alpha law model is a model that I didn't really want to introduce, but some people talk about it. The reason I didn't want to introduce it, it's analytically intractable. So you can't do any calculations with it. And it's not accurate enough to do much with simulations. But yet some people talk about the alpha law model, so we mentioned it. We talked about the BSIM model. How many parameters are in the basic BSIM model? How many in the basic BSIM model? About 195 or something, if you count them, all the model parameters. For one transistor, almost 100 parameters. But that wasn't good enough, because we found out if we make devices with different dimensions, and we extract the model parameters, those 95 model parameters for one device, we take ones a little bit bigger, a little bit smaller, and we extract different parameters. So what we do is we have binning models. And the way a binning model works is you have a device of a certain dimension, it goes and looks and sees which dimensions are closest to a model that it's got, and it pulls that model out. Each one of those models is a BSIM model. So if you have 16 bins, and you have 100 parameters to each bin, you have 1,600 parameters already to characterize the device. But that's not good enough, because sometimes we design a device and fabricate it. We see the threshold voltage a little bit low. If they're a little bit low, transistors are a little bit faster. Or if the threshold is a little bit higher, we want the output a little bit slower. So we have corner models. Oftentimes either 4 or maybe 16 corner models. And each of those corner models corresponds to each bin, corresponds to that 95 parameter transistor model. So at the end of the day, what we have is a model that has several thousand parameters in it. And we still don't have the device well modeled. Okay? So is modeling a transistor easy? So simple. This little 4-terminal device. And yet, we've been working on modeling that device for 50 years. And we will continue to work on modeling that device. Now, one thing that's happening is we're starting to take away the freedom that we're introducing in this course of allowing the designer complete control of the dimensions of the transistor. Because what makes the modeling so difficult is because the characteristics depend upon the dimensions. So we're starting to see processes where they say you can have these transistors, these dimensions, and that's all you can have. And then they get empirical models, they measure model parameters for those transistors. If you want a device that's wider, you put 2 of them parallel. If you want a device that's longer, you put 2 of them in series. Does that make sense? But instead of giving you complete control of the dimensions, they have a small number of devices you can put in parallel or in series. And that circumvents this issue of how do we get a model that accurately characterizes the IV characteristics when you change the dimensions of the device. If you look at the number of papers that are published on modeling the transistor each year, it's probably still going up. People make their careers modeling these transistors. And how do these different models look? And this picture, it's a drawing, but it kind of shows what's going on. So I'm assuming that the black characteristics are the actual characteristics of a transistor. And the blue characteristics are a model that we've used. It could be a level 2 model, a square law model, it could be a VSIM model. And we will extract the characteristics for that model at some point or at some points. Here I'm assuming that I'm extracting at this point. It's pretty easy to extract the parameters so that it goes through that point. Well, what happens when you get away from that point? We start to see the model parameters and the measured parameters differing a little bit. Does that make sense? Things agree here because they extract the parameters to make them agree here, but then they deviate at other locations. I've exaggerated the effect a little bit here, but not too much. Of course, instead of making it go through a point, we could take a group of points and then make it fit pretty good over a group of points, but maybe not perfect at any point. Then where you pick those points and how close you pick them together will affect how good it is locally and how much it deviates away from that point where you extracted the parameters. So here's the problem then. We have 3 currents: the drain current, the gate current, the bulk current. And these two are almost zero. So the modeling problem is primarily to find this function that relates the drain current to the gate to source, the drain to source voltage. That's the primary problem we've got. This kind of summarizes the different models that we've got. And it's not the way we started. We started out here with a simple DC model. And then we extended it and had and included the switch resistance and the gate capacity. We don't know where they came from, we just threw those out. Then we came up and got this square law model. And then we added the characteristics of that square law model to include bulk effects and output conductance effects. And then we came up with the VSIM model and the corner models. And something else we haven't done yet is a small signal model. We need a model of the transistors to tell us what's going to go on if we build amplifiers and so forth. So we'll develop a small signal model. And we will only make a few fleeting comments about a high frequency small signal model. But if you're going to build RF circuits or even baseband circuits, you want to predict what happens as a function of frequency, we need a frequency dependent model. Also, we saw that N-channel and P-channel devices, the approach of modeling was almost identical. If you look at the IV characteristics of an N-channel device, they're in quadrants, into quadrant 1 of the ID-VDS plane. And the IV characteristics of P-channel device are in quadrant 3 of the ID-VDS plane. So normally the drain current is positive for N-channel devices. Normally it's negative for P-channel devices. Normally the drain to source voltage is positive for N-channel devices. It's negative for P-channel devices. But the general shapes are the same. The spacing of the curves are a little bit different, primarily because the mobility of electrons and the mobility of holes are different. This was our square law model. And I'd like to now determine the relationship between our switch level models and our square law models. So last time, Robert looked at the relationship between the switch resistance and the gate to source capacitance for an N-channel MOSFET from the square law model that we've derived. Here's the square law model. And what we observed is when the device is conducting, the switch is on, the transistor is operating in which region? When the transistor is on, we're using the switch. Which region is it operating on? No. We have different names for different regions, but it's triode region. It's deep triode region when it's on. It's where it acts like a resistor. So we have to go down to the triode region equation to look at what the resistance characteristics are. And deep triode corresponds to VDS being very small. So you can neglect the VDS term here. So in deep triode, the relationship between the drain current and the drain to source voltage is the drain current is equal to mu Cox W over L times VGS minus VT times VDS. And this quantity here is the reciprocal of the resistance. Okay? So we assumed in this process mu Cox was 100 micrograms per volt squared. Cox is 2.5 femtofarads per square micron. Where do we get these numbers at? Where do we get these numbers? Mr. Strong, where do we get those numbers?
Process. Manufacturing.
For the manufacturer, the part of the PDK, characters of the process. So the mu Cox, 100 micrograms per volt squared. Cox is 2.5 femtofarads per square micron. Threshold voltage is 1 volt. Supply voltage is 3.5 volts. We're going to set VSS equal to 0. So now we can come back to this equation here and assume it's a device with W and L equal 1 micron. So put W and L equal 1 micron, put mu Cox 100 micrograms per volt squared. When it's on, VGS is going to be VDD. So it'll be 3.5 minus VTH, which is 1 volt. So we know everything in this expression for the FET resistance. And if we do that, whoops, we find that resistance, R switch in, is equal to 4 kiloohms. So our earlier model, switch level model of the device, we said, let's assume that the resistance of the P-channel device is so much and the N-channel device is so much, right? We didn't say where it came from. We know what it is in this process. What did we use before? Earlier in the course.
2 kiloohms, 6 kiloohms.
2 and 6. So we said for this process, it's more like 4. Make sense? So different processes will have different values for the switch resistance and the capacitance, CGS. What's CGS equal to? What?
Normally we use 1.5.
They're right. Again, that was without reference to a process. We just said, let's assume we have a device with these characteristics. For this process, let's see what CGS is. Mr. Day, what's CGS here?
CGS here. Would it be
Yes?
Is it Cox?
Cox?
Whatever area is your device.
Times area, right. Cox times W times L is the capacitance between the gate and the channel with that inversion layer is there. So that's the capacitance density, which is Cox. So in this case, it will be then Cox, which is 2.5 femtofarads per square micron. And the area was assumed to be 1 square micron. So the CGS will be 2.5 femtofarads. A little bit different than we had before. Oh, keep in mind also, though, that I could have changed the dimension of the device. If this device would have been 1 micron by half a micron, then it would have been 1.25 femtofarads. So we see right away then that as we size our devices differently, we will have different switch level models for the device. Is that interesting? Because we saw that the switch level models determine the speed of the device. So this suggests then that as we change the dimensions, we can change the resistances and the capacitances and hence change the speed. Maybe make it faster, maybe make it slower. But we have control of it. Make sense? Okay, so is our switch level model cast in concrete? The answer is no. It depends on the process, and it depends on the dimensions of the transistor you use. Okay? Was it acceptable to neglect that earlier? We didn't tell the whole story earlier, did we? We said, let's assume we've got this switch level model for our transistors. We didn't say that there could be different switch level models when you change the dimensions of the device. We didn't say it was going to be different for different processes, but now we see it is, and we see how to move from the process to the switch level model. For the P-channel device, we do the calculation again, and we see in this case the resistance is 12 kilo ohms, 3 times what it was before because of that mobility ratio, and we see CGS is the same because we have the same dimensions of the P-channel device, and the C-aux are the same. Let me talk briefly about a small signal model. As I said, this is going to just be a precursor. We will spend about a week developing the small signal model for a MOS and a bipolar transistor later. Okay? And here's what the small signal model concept is. The goal with a small signal model is to predict the performance of a circuit or device in the vicinity of an operating point. The operating point is oftentimes called the quiescent point or the Q point. Now, unfortunately, our devices are nonlinear. So this might be the IV characteristics of a one port. Slightly more complicated if we have a transistor because there's 3 terminals instead of 2. We see a nonlinear relationship here. And the small signal model is a model of the characteristics of the device in the vicinity of this particular Q point. I can pick a Q point any place I want. Notice that in the vicinity of the Q point, if I don't know what's around it, it looks linear. So when we develop our small signal models, we will develop linear models around the Q point. We observe that the slope changes as a function of Q point on this example because it's nonlinear. Our small signal models will change with the Q point. Okay. So don't worry too much about details right now. The slope here is one thing, the slope here is a lot different, the slope here is a lot different yet. We can pick different Q points for our device. Let me talk about the process flow. We have looked at the different steps that we can have to put together a process. We do photolithography a lot. We do etching. We do ion implanting. We do growth of oxides. Or we do deposition of oxides. We do CMP. We do a whole bunch of different things, right? So we looked at the things we can do, but we haven't put those together into a process. So it's kind of like having recipes for cookies. You can have a whole bunch of different ingredients, raisins and chocolate chips and a whole bunch of things, and you can put them together in many different ways to make many different kinds of cookies. But you won't know what one particular recipe will yield until you know exactly how it goes together. And you can get entirely different cookies from different combinations of those ingredients. Same thing about a process. Also, if you put a bunch of ingredients together, you want to make chocolate chip cookies, but you put raisins in, you wouldn't expect to see chocolate chips in that in that cookie. So you have to know what the process flow is to know what you can make and can't make and do and can't do in a given process. So for example, can we make a connection between metal 2 and metal 1? Or can we make a connection between metal 1 and substrate? Or can we make a connection between metal 2 and substrate? Those are all valid questions to ask. And we can put processes together that allow us to do any or all of those things or none of those things. It's only after we know what the process flow is where we will know what we can do in that process. Make sense? So we need to know what the process flow is to know what we can do. In the laboratory, we've kind of can guess at what we can do because we have certain design rules. And you can go backward and say, well, if there's not a design rule relating to something, I probably can't do it. But we haven't told you where those design rules come from or what the process flow was to get those design rules from. Does that make sense? So we're going to talk about the process flow today. And every process will have a flow like this. So it's hard to get these details. Companies typically don't want to share details, so these are real details for an in-well process that I won't tell where the rules came from. I was visiting a company and said, well, why don't you use this as kind of an example? But I think it was for the process they were running or had run somewhat recently. So here's the process steps. We talked about these before. And we see 24 steps here. Clean the wafer, growth in oxide, apply photoresist, pattern in-well with mask 1, and so forth. So we're going to put together a process with this recipe. This is a recipe for an in-well CMOS process, very similar to the ones we're looking at in the laboratory. And I list here 55 steps. What if you mess up one of these steps? What if you mess up one of these steps?
Can you strip it?
What?
Can you strip it?
Usually not. Once in a while you can mess up a step and redo it. Most of the time you mess up a step, you have a wafer breaking party. And you're not popular if you break wafers. Okay? So bottom line is, every one of these steps needs to be accurately done in the right sequence. You mess up any one of the steps, and usually you have to throw your whole partially completed wafers away. So this is an in-well process. I'm going to only show a single metal in the slides that follow, and it's a 2-poly process. Some processes have 2 polys, some have 1. This type of process dominates what's used for high-volume, low-cost processing of ICs today. We have a lot of variants of this process. Most of those variants cost more money. So most of your low-cost ICs, the ones that are differentiated primarily on price you charge for your product, will be in a process like this. I could talk about lots of different processes. In this course, I'm going to focus primarily on processes that are meant for high volume production. For those of you who get jobs in companies, some companies have very specialized processes, often have very, very expensive processes for particular product lines. I'm not interested in those, in looking at those other processes. I'm interested only in the high volume, low cost processes. By the way, the way you approach the design of those processes is very similar. I'm going to look at an N-channel MOSFET, a P-channel MOSFET, a poly resistor, and a double poly capacitor. Primarily, this process is set up for making N-channel and P-channel MOSFETs, but a poly resistor and a double poly capacitor come along fairly easily. There are some other niche devices available in that process as well. Here's a top view. And this top view probably makes sense from what you've been doing in the laboratory. And as I put this process together, I'm going to look at the process as it goes together along 2 cross sections, the A prime and the B prime cross section. Okay. The well contacts and the guard rings, I'm going to discuss those later. Here are well contacts around here. This also forms a guard ring. I'm not going to focus on those in this discussion. So I've removed the guard rings and the contacts now. And so I've simplified the drawing a little bit. And what we see in the lower right is the N-channel MOSFET. What we see on the source and the drain are right here. What we see in the lower left, excuse me. I think, is the P-channel MOSFET. What we see in the upper left is the capacitor, and what we see in the upper right is a poly resistor. Okay, so we're going to see how those devices are formed. So the first thing I'm going to do is look at patterning the end well. Of course, this is the first thing that occurs in this processing flow. We start with a wafer, we clean it, we grow thin oxide, we apply photoresist, we pattern the end well, develop the photoresist, deposit and diffuse N-type impurities, and strip the photoresist. So I'm going to go through those steps right now. So I've highlighted the end well mask. This is gold here. These other masks wouldn't be present yet, so I've dimmed them because they're coming later. So on the first mask, you just have an opening, and the opening would be inside this gold region here. So here's the mask features. We don't see that mask on the AA prime cross section because there's no end well underneath this material on top. So I'm going to look both a top view and a cross-sectional view. So we start with a blank wafer. This is the top view, and it's P-doped substrate. So if you look down at the wafer initially, before you do anything, you'll just see P-type material. Okay. And then we covered it with photoresist. Photoresist is about a micron thick. It's kind of a viscous liquid when you put it on, and then you bake it so it's hard. I'm going to use posi-photoresist. That is, the exposed regions are going to be soluble in the developer. So here's where the mask is at. So the exposed regions are soluble. So what I'm going to do is expose this region here then. And when I develop it, the photoresist will disappear inside here. I could also use negative photoresist to make this feature. You could do it either way. But I'm doing posi-photoresist. So when I expose it, I make the region here soluble. Okay. And then when I develop the photoresist, it will be removed where it's soluble. So if I develop it, I'm going to see P-type substrate underneath the photoresist that was here. The rest of the wafer still has P-type material underneath it, but I can't see that from the top because that's covered with photoresist. Okay. Then I do an ion implant. Ion implant is non-selective. I do it over everything. But that ion implant, the ions are going to get stuck in the photoresist where the photoresist is at. So they won't make it down to silicon. Only those areas that are not covered with photoresist will have the silicon surface affected by the implant. So when we get done stripping the photoresist now, we will see N-type impurities in this region here, P-type impurities in this region here. Make sense? Now let me look at the two cross sections, AA prime and BB prime. If I look at the two cross sections, again, I'll put the process together here, go through the same steps. What did I do first? I put photoresist on. And then what did I do? I masked it. So this was the mask that was put on. Actually, there's a reticle, but we'll assume it's a mask. And then I exposed it. When I exposed it, I changed the properties in this region here. It was exposed. So when it's developed, that will disappear. So now I develop the photoresist. And now I see an opening here. But I see no openings on the top because I didn't expose any of that along the AA prime cross section, or along the AA prime cross section. Then I do an implant, and the implant puts impurities in the region that's open, but it gets stuck in the photoresist. And then when I strip photoresist, I end up with something like this. Wow. First step in the recipe, the Inwell. So here's our Inwell. Now, it might be the case that we do a drive-in diffusion here. The impurities don't go that deep when we implant them. Then we typically heat it up and let the impurities go down a ways. So I'm not going to worry about whether they've been driven down yet or not in this presentation. Next thing we do is go to Mass 2. And Mass 2 defines the active area. And the active area is those areas that are going to become drains or sources or gates of the transistor. Apply silicon nitride, apply photoresist, pattern silicon nitride, develop for photoresist, etch silicon nitride, strip photoresist, grow field oxide, strip silicon nitride, strip thin oxide. So a lot of steps along here. So here's the active. Active will show up here, which is going to be the P-channel transistor. It's going to show up here with the N-channel transistor. Notice we do them both at the same time. So the active mask looks like this. If you look at a cross section, the active mask is going to create an opening in this region here and this region here. We grow field oxide in the complement of the active region. So there's field oxide on top here and field oxide on top here. And all the way across here, there's field oxide on top. Any questions so far? I should point out what this field oxide is doing. We're going to eventually run metal around to interconnect things together. Anytime you run a conductor on top of a dope region, you try to pull impurities to the surface. You try to create an inversion layer. If you have your metals close to the silicon, then when you put a voltage on the conductor, it will create an inversion layer and short everything out. So what we do is we put the insulator on, so our conductors are way above the surface, so that the capacitance between the gate and the silicon is so low that we don't get enough force to create the inversion layer. So the field oxide then provides isolation between devices. It provides isolation by essentially raising the threshold voltage up to a very high level. Make sense? Next thing I'm going to do is put the gates on. Notice that I do the gates for the N-channel and the P-channel device at the same time. So here's the poly masks, poly 1 mask, and this the purple here, I guess. And so it's supposed to all be the same color. That's supposed to be poly 1 on the top too. It looks like it's a different color, doesn't it? So the poly is going to form one plate of a capacitor. It's going to form the P-channel MOSFET, the N-channel MOSFET, and the resistor. Now, I'm not showing the photoresist, the exposure, and the development, but after I put the thin oxide down, then I put poly on top, I pattern the poly, and when I'm done, I see poly on top of the active region here, separated by thin oxide. This is going to be our P-channel transistor. I see poly on top of thin oxide here. This is going to eventually be our N-channel transistor. And I see poly on top of a thick insulator on top of thin oxide. This is really thin, so we really can't see the presence of this. So here's poly on top of field oxide, basically. And here's poly on top of field oxide. So that's called the gate oxide. That's a real thin layer of oxide. That's a critical processing step. If you go back and look at the process flow, before we put that down, we first stripped oxide, etched it away, so we have silicon. Then we put the thin layer, it's going to be our gate oxide on, and then cover it with poly very quickly. Make sense? That's one of the most critical steps in this process. So here's our gate oxide under here and under here. I should point out, I should emphasize that they're made at the same time. And since they're made at the same time, what does that tell us about COX for the N channel and the COX for the P channel transistors? It should be the same, because we make the oxide at the same time. Could we do them separately? Yes. And if we did, we could probably change the threshold voltage of the devices. Is there an advantage for doing it at the same time? Cheaper. One processing step gets them both at the same time. And for some circuits, there's an advantage of having a match as well. When we do it at the same time in most processes. This is a double poly, so if we have a second poly layer, we're going to put the second poly on top of the first poly here to form our capacitor. And so we'll have that poly 2 mask. When we're done, the only place it appears is on the top here. So now we see poly 1 and poly 2 separated. I didn't look on the recipe, but there was a thin oxide that was grown before you put poly 2 down. So we also have thin oxide between poly 1 and poly 2 to get the capacitance density up. Now we're going to pattern the P-channel drains and sources with mask 4, and we're going to pattern the N-channel drain and sources with mask 5. So we have a mask to determine what's P-channel and what's N-channel. We call these P-select and N-select when we're putting a process together. The P-select match tells where P-channel devices are going to be formed. The N-select mask tells where N-channel devices are going to be formed. And these are typically non-critical masks. They have to be there, but their boundaries can be sloppy and will still form the transistors correctly. So here's P-select. The P-select is only going to be here because here's where we want to make the P-channel transistor. Notice it's much bigger than the active. Here's the active region. It's much bigger than the active. It just can't be so big that it overlaps where the inactive is at. It can be a lot bigger than the P active. It just can't overlap the inactive. So that's that P-select mask. And so what we do then is we do an ion implant through the opening of the P-select mask. The only place that it's exposed, this recipe covered with photoresist. The only place that is exposed to silicon is here and here, so that gets the P-type impurities. Notice over here we haven't done anything yet, because this would have been covered with photoresist when we had the P-select mask on. We don't want to do anything over here because we're going to form, what are we going to form here? Our N-channel transistors. So there's a P diffusion that forms the P-channel transistor. There's a very interesting property that these devices have. This is called a self-aligned process. Notice that the gate blocks the implants from going underneath the gate when you do your implant. So if you're doing your implant, the impurities can't get into the silicon here because there's a gate on top. If you were to have an alignment problem, and this was to move back or forth a little bit, no matter where you place it, as long as you don't move it a long ways, you'll still correctly form your transistor. Okay? So a process that has that characteristic is called self-aligned. The drain and source are aligned relative to the gate. The alternative could have been to have a mask opening that was this wide. And then we exactly put the source where we want it. And exactly put the drain where we want it. Then if you didn't have alignment of the drain and the source, you might have a gap on this side or a gap on this side. Does that make sense? So we could have put this process together and not have it self-aligned, but our yield would probably be bad. So now we cover everything with photoresist again and open up the N-Select side. And then we do an N-type implant, and we form the source and drain of the N-channel transistor. Again, it's still self-aligned. I should have shown the PD fuse. The PD fuse is already done, so the PD fuse should be showing here as well because it's been put in. Then we're going to do contact openings. So these are going to be the contacts that we have. We're going to see some of them on this BB prime cross section. Here's the source and the drain of the P-channel transistor. Here's the source and the drain of the N-channel transistor. This gate connection we won't see on this cross section. And I guess up on top here, I'm going to see on this A prime, I'm going to see one of the contacts to poly 1, and I'm going to see contacts to one end of the resistor in this cross section. So here's what the contact mask looks like. What's the difference between contacts and vias? Yes?
Ideas generally just used to connect one layer to another, and contacts are used to connect to the outside world.
Good conjecture, but not quite. Pads are used to connect the outside world. Vias and contacts really mean about the same thing. Contacts are things that typically connect to an active region. Vias connect metals to metals. So they're still narrow holes, same size. They're really about the same thing, just what you connect to. Okay? Pardon?
You said metal to metal for the vias?
Yeah, vias for metal to metal. Metal 2 to metal 1. Metal 3 to metal 2, and so forth.
Don't we make a M1P via?
What?
What about the M1P via? Isn't that metal 1 to poly?
Metal 1 to poly, is that called a via, or is that called a contact?
I don't know, it's in the vias on cadence.
So it must be a via then. So I cover the whole surface with silicon dioxide to make it insulated around everything. And then I pattern the silicon dioxide so I have an opening here and an opening here, which I eventually want to connect to the source and the drain of the P-channel transistor. I have an opening here and here, which I want to connect to the source and the drain of the N-channel transistor. I see an opening here where I'm going to connect to this poly 1, and an opening here where I'm going to connect to poly 1. So I'm going to put metal over everything. So I apply metal and then pattern the metal. Now here's the metal 1 mask. I thought it was blue. Here's the metal 1 mask. So I put metal, whoops. And when I put metal across I have metal going down into here, and metal going into here, and metal going into here, and metal into here, and metal into those places there. I don't see the interconnects with metal because they don't show up on these cross sections. So now we see how we formed the N-channel and the P-channel MOSFET, the resistor, and the capacitor. So you can now know what you can create from this recipe. Okay? And what have we used to put this together? Well, there were 50-some process steps. I kind of only went into details on about the first 5. Then I suppressed a lot of the details on the others, where the applying and stripping the photoresist and so forth. So now we know what we can do in this process. Can we connect? Well, we'll ask this question in a bit. Can metal connect to active? The answer is yes. We had a via that was formed before we put metal 1 down, and that via can go to active. Can metal connect to substrate on top of field oxide? The answer is no, because we put field oxide on before we put the metal on. And there's no opening. We can go through that thick level of oxide to make contact to the substrate. How can metal be connected to the substrate? Well, the way to connect metal to substrate is to put an active region in first. That way you've got no field oxide there. Then you can connect, and you'll make that P active. So you'll put P active opening in the area that you want to connect the substrate, and then you can make a contact to it. Are you with me? Can poly be connected to active underneath the gate? And the answer is no. There was no opening. There was no via that was put in before we put that gate oxide down. So you can't make a connection from active to the channel underneath the gate. Can poly be connected to active any place? The answer is, what's the answer to that? The answer is no. We have to connect poly to metal and then metal to active. We can't make a direct connection between poly and active. Can metal be placed under poly to isolate it from the bulk? Would that be nice to do? Put metal underneath poly? Can we do it? No, poly went down first. So we can't get metal underneath poly. Can metal 2 be connected directly to active? The answer is no. If you go through the process flow, there's no via that will allow you to connect metal 2 to active. You have to connect metal 2 to metal 1, and then metal 1 to active. Can metal 2 be connected to metal 1? The answer is yes. And those are with vias. Can metal 2 pass under metal 1? Nope. Metal 2 always goes on after metal 1, so it can pass over but not under. Could a process be created that will result in an answer of yes to most of these questions? Yeah, we could do it if we wanted to. Whether it would be an economical process or not, I don't know. Yes?
Why can't you connect poly to active? I'm having a hard time.
When we put poly down, all we did was put thin oxide down, then we put poly on immediately. There was no via or opening that allowed us to connect poly to active. There was always thin oxide underneath it. Okay? It's a good question. You have to go back and look at the recipe. I gave this slide at the beginning of the course. I said there should be a point in the time where all these things come together. I think we've talked about models, we've talked about processing steps, we've talked about layout, we've talked about device characteristics. This is the point that all of these things should be together now. So if you don't see how these all fit together, then please come by and talk to me. Because this is kind of what we need to close the loop, looking how the process flow goes together. What time is it? Got a quick question. How does an inverter delay compare between a 0.5 micron and a 0.18 micron process? So we can go to a 0.5 micron process, pick out the threshold voltages, pick out mu Cox, pick out Cox, and we do the same thing for a different process. And so what I've got is the threshold voltages, the mu Cox's for these two different processes. And if you look at T high low and T low high, they're all R pull down and R pull up times CL. And we, at the beginning of the period, we talked about what the R pull up and R pull down are. So we can calculate what R pull up and R pull down are for the 0.5 micron process and for the 0.18 micron process. We see there's a fairly big difference in the resistors for those two different processes for devices of the same relative dimensions. And in particular, if you look at T high low plus T low high, you'll see that the 0.5 micron process is about a factor of 2 slower than the 0.18 micron process. I think that's where I wanted to stop. Are there any questions? That's all for today. Thanks. If there are any homework scores that got passed around, I will take them back. Thank you.